10, 9, ignition sequence starts. 6, 5, 4, 3, 2, 1, 0. Liftoff. We have a liftoff.
Astronauts who went to the moon during the Apollo program traveled on a Saturn V with a launch weight in excess of 2.8 million kilograms. The command module, far less than 1% of the launch mass, returned to the Earth. The shed stages and even the charred capsule could not be reused. Spaceflight was very expensive. In the early 70s, the Nixon administration favored a reusable space transportation system, commonly known as the Space Shuttle. It was expected to reduce costs and provide regular access to space for paying customers.
5, 3, 2, 1, 0, and liftoff of Space Shuttle Atlantis.
NASA had to develop new high-performance reusable main engines, advanced avionics, and a reusable thermal protection system to enable the orbiter to make repeated re-entries into the Earth's atmosphere. Development of these technologies proved to be very challenging. The very earliest proposals for spaceflight had imagined a winged spaceship returning to the ground to be used again. At its foundation, NASA's Space Task Group had inherited the X-15 rocket-powered research aircraft. It was the result of a study made by Walter Dornberger, commanding officer of the German V-2 development program. The X-15 was intended to gather data about hypersonic speeds and very high-altitude flight. Essentially, it was a fuel tank and a rocket motor with short wings and a cockpit. It was fueled with anhydrous ammonia and liquid oxygen, with highly concentrated hydrogen peroxide driving the turbopumps that delivered the fuel and oxidizer. The engine could be throttled by varying the speed of the turbopumps. The X-15 began operation in 1959 as a partnership between NASA and the US Air Force, which was keen to develop a space plane. Mounted beneath the wing of a B-52, it was carried to more than 13,000 meters before it was air-launched. The X-15's engine would fire for around 1 minute. At the peak of high-altitude flights, the pilot had no aerodynamic control. The plane had thrusters for basic maneuvers above the atmosphere. When the fuel was depleted, the craft returned to a dry lake bed in the Mojave Desert. Data gathered during this unpowered return to Earth was of huge benefit to the developers of the Space Shuttle, which had to make similar high-speed, dead-stick landings. Some of the X-15 pilots became household names, including Neil Armstrong, who made 7 X-15 flights, and the aircraft contributed significantly to the manned space program. Yet, even as the X-15 flights continued, NASA and the Air Force began testing a new lifting body concept that held out hope for the shape of spacecraft to come. In 1963, a plywood wingless demonstration aircraft began flights towed behind a Pontiac convertible. They called it the flying bathtub.
3, 2, 1, 0.
At this time, NASA was committed to the ballistic re-entry concept necessary for the blunt body, heat shield type of spacecraft being built for the Mercury, Gemini, and Apollo programs. This meant a fleet of naval ships had to be on standby in each of the major oceans when a spacecraft was launched, which was very expensive. The Kennedy deadline was approaching, and the Apollo program was reaching its climax. The huge and very expensive Saturn V had taken a crew to lunar orbit in 1968. And then both Apollo 11 and Apollo 12 made successful lunar landings in 1969. Apollo missions extending out to Apollo 20 had been scheduled. But at this point, the last 3 missions were suddenly cancelled. The White House was back in Republican hands. And the new president, Richard Nixon, although he was keen to bask in the reflected glory of the Apollo astronauts, also wanted to save money.
That this is the beginning of a new era.
After the return of the hugely successful Apollo 15 mission, Nixon tried to scrap the remaining Apollo program, but was persuaded by the director of the Office of Management and Budget to let NASA finish its last 2 lunar missions. It was obvious that NASA's blank check days were coming to an end. NASA and the Air Force had continued to explore the lifting body concept with flight tests of the much heavier HL-10 starting in 1966. It was built to NASA specifications by Northrop. The hope was that a new generation of spacecraft could re-enter the atmosphere and land at a designated strip, saving the costly mid-ocean recovery. The HL-10 was equipped with a small rocket motor and was air-launched, just like the X-15. Telemetry allowed a ground team to monitor the craft's behavior. Ultimately, the HL-10 reached heights in excess of 27,000 meters and a speed of Mach 1.86. Again, the most valuable data gathered during the HL-10 program came from the unpowered return phase of flight. Like the X-15, it dropped rapidly while generating very little lift, just like a spacecraft. When the lifting body program concluded in 1970, it was just one of many concepts being investigated by NASA and the US Air Force. Various companies hoping for lucrative contracts were also submitting designs. NASA had wide-ranging ambitions for the post-Apollo future, but the Nixon administration, which had continued cutting funds for the space program, directed the agency to focus on low Earth orbit with a reduced budget. Some of the scrapped Saturn V launchers were repurposed for an orbital space station that became known as Skylab, while the remaining Saturn rockets became billion-dollar museum pieces. Skylab successfully demonstrated the value of an orbiting laboratory. Pure crystals were grown in microgravity, and a solar telescope enabled new studies of the Sun. But without means to boost Skylab's orbit, it could only ever be a temporary outpost. NASA began planning a more permanent space station for the distant future. Its construction would rely on a new spacecraft called the Shuttle. It might be expensive to develop, but ultimately it would cut the cost of access to space. The various concepts featured 2 stages. a booster that would fly back to the launch site, and an orbiter that would fly back to the ground at the completion of the mission. All were too expensive for the administration in Washington. Finally, a compromise design was reached. Relatively inexpensive solid-fueled boosters would serve as a first stage, and the orbiter would have a huge external tank that would be discarded nearing orbit. But it took years for the concept to be tested to the point where plans could be drawn up. Lockheed had devised a lightweight thermal tile with such promising insulating properties that it made the winged concept feasible. Single-use capsule spacecraft had a heavy phenolic resin heat shield that burned away during re-entry. A reusable spacecraft needed a reusable heat shield, and Lockheed's lightweight silica tiles meant heavy, heat-resistant titanium alloys could be dispensed with in favor of a more conventional aluminium superstructure protected by the tiles. NASA was collaborating with the Air Force on the new spacecraft, and because of military requirements, the design was much larger than most of the early concepts. Work began on the first shuttle in 1974. Initially named Constitution, it was intended for approach and landing tests within the atmosphere. It lacked a heat shield and engines. It was first seen in public at a ceremony as it was rolled out of the Rockwell plant in California. A letter-writing campaign had convinced NASA to rename it Enterprise, after the spacecraft in Star Trek, a TV show that enjoyed modest success at the time. The Enterprise's first trip was by road to the Dryden Flight Research Center. It took 10 hours for the spacecraft to make the 58-kilometer journey to begin a series of captive flights known as approach and landing tests. The Enterprise was unable to fly without assistance, so NASA had purchased the surplus 747 from American Airlines. It had been reinforced with special attachment pylons and extra stabilizers added. At Dryden, a complex framework had been constructed to lift the shuttle onto the back of the airliner. 4 astronauts, in 2 crews, would carry out the first test flights. Fred Hayes had flown on the Apollo 13 mission. His co-pilot was Gordon Fullerton. Joe Engle had made 3 X-15 flights, and his co-pilot was Dick Truly. Enterprise did not have thermal tiles. Instead, it had a dummy fiberglass coating, and it was fitted with a nose spike housing an airspeed indicator. Tests began in 1977. A series of taxi runs, followed by captive flights, were made to confirm designers' expectations. Initially, a tail cone was fitted to reduce turbulence around the rear of the spacecraft. In August, Enterprise made its first free flight. With the carrier aircraft in a shallow dive, the shuttle was easily able to pull away and fly autonomously. The new spacecraft handled well. Four successful free flights followed.
We're at the end of the approach and landing test phase of this program, but it's really not an end at the beginning. It's just a small step really accomplished toward getting the orbiter into space, and then in that aspect, I'm looking forward to more of the same exciting times as we continue on toward that first orbital flight.
Back at the Rockwell plant, a second spacecraft was taking shape. Columbia would be the first space-worthy shuttle. It was being fitted with thermal tiles and the new RS-25 engines. Both were giving trouble. The glue being used to stick the tiles to the aluminium skin of the aircraft was failing within hours. The radically new engines operated more efficiently because of their much higher chamber pressures. But there were developmental problems. Because the shuttle main engines were positioned off-center relative to the external tank and solid boosters, they had to be able to pivot over plus or minus 10.5 degrees in both axes, as the shuttle stack dropped stages and as fuel was depleted. During the first 2 minutes of flight, the major thrust would come from the solid rocket boosters. These too had to have vectored thrust, and the nozzles could move through plus or minus 8 degrees. Again, Columbia had to be transported by road to the Dryden Flight Research Center to be loaded onto the carrier aircraft that would take it to Florida. It was obvious that difficulty with the thermal tiles had not yet been solved. Columbia landed at the Kennedy Launch Center in 1979. While it had arrived with only a partial covering of tiles, tests revealed that even those tiles would have to be removed and reapplied after a densification process. Shifts of technicians working around the clock took 20 months to complete this process. Meanwhile, the first external tank was shipped from the Michoud Assembly Center in Louisiana. It was painted white to protect its outer layer of insulation from ultraviolet damage. By 1980, the shuttle main engines had emerged from their long developmental phase, achieving NASA's specification of 65,000 seconds of testing. Requirements for the engine to be reusable and be capable of throttling down to 65% had been met. The first 3 engines arrived at the Cape and were fitted to Columbia. The original launch date had been delayed by 2 years. At the end of 1980, Columbia rolled out of the vehicle assembly building for Pad 39A. Before it could fly, it had to complete a final certification test that included a 20-second firing of the 3 main engines.
9, 8, 7, 6,
Officially known as the
5,
wet countdown demonstration test, it verified all the systems on the ground and in the spacecraft.
And we have had shutdown of all 3 engines.
Astronauts John Young and Bob Crippen would fly the first mission. It would be the first time a new spacecraft flew with a crew on board. On April the 12th, 1981, Columbia was ready to fly.
T-minus 10, 9, 8, 7, 6, 5, 4. We've gone for main engine start. We have main engine start.
The first 4 flights would all be devoted to testing the spacecraft, and the flight profile for the first mission was designed to minimize stress on the orbiter. The payload bay was empty except for a flight recorder that captured data from an array of sensors. NASA needed to understand the difference between theoretical predictions of the orbiter's behavior and its actual handling. The payload bay doors had heat-dissipating radiators on their inner sides to keep the orbiter cool. When they first opened, the astronauts were surprised. At launch, an overpressure wave had damaged lower areas of the orbiter, including thermal tiles. Young and Crippen maneuvered their craft into a position that allowed a US spy satellite to photograph its underside, but no tile damage could be seen. All the orbiter's basic functions were verified over the 2-day flight, and the craft returned safely to runway 23 at Edwards Air Force Base.
5, 4, 3, touchdown. Welcome home, skipper. Welcome home, Columbia. Beautiful, beautiful.
Columbia's first mission was declared a success, with Crippen and Young having nothing but praise for the new spacecraft. The shuttle was readied for its flight back to Florida, where it would be prepared for its next launch. And there was a long list of worrying anomalies that would have to be addressed before Columbia could fly again. Columbia was towed from the landing strip to the processing facility at the Kennedy Space Center. This first ever preparation of a spacecraft for its second flight to space was to be meticulous. As well as the scheduled tasks, like refurbishing the main engines and checking the thermal protection, the orbiter was checked for damage. Spacecraft tend to evolve. If something breaks or malfunctions, it is not repaired, it's redesigned. Columbia was already lighter than the Pathfinder Enterprise, and engineers building Challenger, the next shuttle, were already incorporating improvements. As a result of anomalies encountered on the first shuttle flight, Columbia and its emerging sister spacecraft were all modified. The most pressing issue was the loss of 16 thermal tiles and damage to a further 148 from shock waves during launch. The shock had bent Columbia's body flap so far out of alignment that engineers were surprised it still functioned. This resulted in extensive redesign of the sound suppression system at Pad 39. A 1 million-litre water tank was built that began flooding the flame pit 6 seconds before the main engines were started, reducing the impact of reflected shock waves. It took 7 months to prepare Columbia for its second flight. The initial aim was to have a 2-week turnaround, but engineers knew there was still a lot to learn about their new spacecraft, and as yet there was still only one shuttle rather than a fleet of 4, which was still taking shape.
Countdown now being conducted by...
The second flight began in November 1981. It was the last time the external tank was painted white. Originally as protection against the sun, the paint was not needed, and leaving the tank its natural orange color saved almost 300 kilograms.
We have the main engine start. And liftoff. Liftoff of America's Space Shuttle, and the Space Shuttle has cleared the tower.
Astronauts Joe Engel and Dick Truly had not flown in space before, and on the ground, Sally Ride became the first female Capcom. While a failed fuel cell caused Columbia's return after 2 days instead of the scheduled 5, the mission was regarded as a success. After 2 more test flights, also with Columbia, the shuttle system was declared operational. Yet there were problems still unsolved. After the second flight, examination of the boosters recovered from the Atlantic revealed an O-ring, used to form a seal between segments, had partially burned through. Tests were made, but designers felt it was not a problem. Pieces of foam breaking free from the external tank were also regarded as a system idiosyncrasy that could be accommodated. By 1985, 3 new orbiters had entered service, making up the full complement of 4 space shuttles. The Space Transportation System was a complex blend of technologies that had to function together with great precision. Together, they were known as the shuttle stack. The largest component, the external tank, was the only disposable part of the system. It was coated in a spray-on insulation, necessary to keep its cryogenic propellants from boiling. The orbiter and the 2 solid rocket boosters were mounted on the tank. When fully fueled, this was the heaviest part of the shuttle stack. 4 minutes before launch, the main engines went through a final gimbal test. At T-16, the pad deluge system was activated. With 10 seconds to go, the hydrogen burn-off system was activated, and then the main engines ignited. At 0, the solid rocket boosters were ignited, and the explosive bolts that hold the shuttle stack to the pad detonated. At launch, most of the thrust was provided by the solid rocket boosters. Once alight, they couldn't be extinguished. The shuttle's 3 main engines were fed with liquid hydrogen and oxygen through umbilicals near the rear attachment points. After rolling to a heads-down position, the stack would continue climbing along an easterly path till 2 minutes after launch, when the boosters burned out and were discarded. Eight minutes after launch, the main engines shut down and the empty external tank was discarded. It would re-enter the atmosphere and burn up over the Indian Ocean. At this stage, while the shuttle was above the atmosphere, it still needed a further boost to maintain orbit. At the high point of its elliptical path, the orbital maneuvering engines were fired, putting the craft into a circular orbit around 320 kilometers above the surface, depending on the mission. The first 3 years of operational flights saw the new shuttle fleet at the center of the satellite launch business. Almost every mission included at least one satellite deployment. NASA planned to phase out conventional rockets, which it assumed would be priced out of the launch business. During its first 3 operational years, the shuttle fleet deployed 30 satellites. Late in August 1983, STS-8 was the first night launch. The mission went well, and the boosters were recovered from the Atlantic in what had become a routine exercise. Analysis revealed severe erosion of the nozzle on the left booster. Estimates determined it was just 20 seconds away from failure. But it was treated as a minor incident, with shuttle flights continuing to be scheduled at an increasing pace. NASA was encouraging the idea that spaceflight had become routine. In February 1984, Challenger launched with 2 communications satellites aboard. Palapa B2 and Westar 6 were set loose, but the payload assist boosters on each satellite failed. They remained trapped in low Earth orbit. Additional time on every flight was devoted to new techniques made possible by the new system. On STS-41B, Bruce McCandless became the first person to use the new manned maneuvering unit. Since the Gemini program, attempts had been made to have an astronaut fly in space independently, but they were abandoned because of the danger. Several missions later, Discovery was to deploy 2 more satellites. Lloyd's of London had partially funded this flight. As the insurer of Palapa B2 and Westar 6, the company had met its obligation to its clients and now owned the wayward satellites. Previously, they would have been space junk, but NASA would use the MMU to retrieve the satellites and bring them back to the ground. Engineers feared a collision between the shuttle and the heavy satellite, so the idea of approaching Palapa B2 using the manned maneuvering unit felt like a good solution. Astronaut Dale Gardner carried a capture ring that enabled him to slow the satellite's spin. The plan called for Palapa to be grappled by the shuttle's robotic arm, but this proved difficult. The spacewalkers had to improvise. It was brought into the cargo bay by human muscle power. Westar 6 was captured the same way. While the recoveries were successful, NASA decided that brute force capture method was too risky. Subsequent missions began attaching an astronaut to the robotic arm via foot restraints.
"30 seconds until touchdown."
Discovery returned to the skid strip at the Kennedy Space Center, the first time satellites had been brought back to the ground. In 1985, Atlantis became the 4th and was expected to be the final spacecraft in the shuttle fleet. In that year, the greatest number of shuttle flights, 9, were made. And it was expected that the rate of shuttle missions would continue to accelerate. NASA was confident that ongoing issues with damage to the thermal protection tiles and the shedding of insulating foam from the external tank were understood and were more of an annoyance than serious problems. In California, facilities at the Vandenberg Air Force Base were being readied for shuttle flights. The site was ideal for launches to the south for polar orbits that were useful for intelligence satellites. The military was impatient with the slow rate of shuttle launches, and pressure grew to keep expendable rockets in service.
Liftoff of Atlantis. A new orbiter joins the shuttle fleet and it has cleared the tower.
Atlantis' first flight was a classified military mission. It deployed 2 spy satellites and was declared a success. Its second mission was notable because the processing between flights was the fastest to date. Again, NASA expected the turnaround time between flights to continue to shrink. Earlier in 1985, Vice President George Bush announced NASA would send a teacher to deliver lessons from space.
Congratulations, Krista McAuliffe.
Yet another sign that spaceflight was becoming routine. Krista McAuliffe and her understudy Barbara Morgan began training for SDS-51L, scheduled to fly early in 1986. McAuliffe was popular with the news media, and NASA was delighted at the positive publicity generated for the Teacher in Space project. The plan called for McAuliffe to conduct 2 lessons from space, including a tour of the shuttle Challenger. They would be broadcast live to classrooms across the United States. Challenger would launch in mid-winter, and though the Kennedy Launch Center is in sunny Florida, conditions were bitterly cold. In the hours leading up to the launch, engineers tried to convince managers the mission should be delayed. Previous cold weather launches had shown damage to the seals in the solid rocket boosters, but 24 successful missions led management to have faith in the system. Challenger's mission would proceed, though no shuttle had ever launched at such low temperatures.
9, 8, 7, 6. We have main engine start. 4, 3, 2, 1, and liftoff. Liftoff of the 25th Space Shuttle mission, and it has cleared the tower.
Cameras on the crowd singled out Edward and Grace Corrigan, Krista McAuliffe's parents.
Challenger, go with throttle up. Challenger, go with throttle up.
All 7 astronauts perished. At this point, McAuliffe's parents were still unsure what they had seen. The shuttle fleet was grounded, and moves began to establish a formal inquiry. 3 days after the disaster, President Ronald Reagan spoke at a memorial service for the Challenger crew.
The dedicated men and women of NASA have lost 7 members of their family. Still, they too must forge ahead with a space program that is effective, safe, and efficient, but bold and committed. Man will continue his conquest of space, to reach out for new goals and ever greater achievements. That is the way we shall commemorate our 7 Challenger heroes.
The president was resolute. The shuttle program would continue. The Rogers Commission, set up to find the cause of the disaster, determined that extreme cold had made a seal in the right solid rocket booster fail. But the inquiry also determined that NASA management tended to exaggerate reliability to the point of fantasy. The remaining shuttles were placed in storage, and plans for the Vandenberg launch site were scrapped. There were just 4 American satellite launches for the remainder of 1986 and 87. Major research probes, like the Galileo mission to Jupiter, were postponed indefinitely. Plans were made to return to expendable rockets. There was an extensive redesign of the shuttle's boosters, and every aspect of the space transportation system was scrutinized. Astronauts would return to wearing pressure suits during launch and landing, and a limited escape system was made available.
Go for main engine start. 7, 6, start. 3, 2, 1, 0, and liftoff. Liftoff. Americans return to space.
When Discovery made the return to flight mission in October 1988, it did so with severely diminished expectations. It released a tracking and data relay satellite, replacing the one destroyed with Challenger. It was necessary communications infrastructure for the shuttles and future science satellites. After Challenger, there would be no more deployment of commercial satellites. The shuttle's money-making days were over. There was one positive for the shuttle system. A new spacecraft was built to replace Challenger. It was given the name Endeavour. The second flight after the Challenger disaster was a classified military mission made by the shuttle Atlantis. Launch footage suggested that a piece of a booster nose cap had come away, and Commander Robert Gibson was asked to use the camera at the end of the robotic arm to check for damage.
I said to myself, we are going to die, because I was looking at more than 700 shredded tiles on the right wing of Atlantis.
Gibson was given instructions to land in the usual fashion. Whether flight controllers on the ground did not appreciate the problem or they knew that nothing could be done, remains unclear. Even as it landed, white marks on the usually black tiles suggested damage. The full extent of injuries that Atlantis had suffered only became apparent on the ground. 700 thermal tiles were affected, with one tile in a critical area completely gone. The incident received very little publicity, and the shuttle program would continue. The Hubble Space Telescope had been waiting in a clean room since the year of the Challenger disaster. It was costing NASA and the European Space Agency $6 million a month to keep it in storage. It had been designed with doors that could be opened in space, so it could be repaired and upgraded. It would just fit into the shuttle's cargo bay, and it was completely reliant upon the Space Shuttle to deliver it to orbit and to carry out routine servicing. On April the 24th, 1990, Discovery sat on pad 39B about to begin its 10th mission. Hubble would finally be deployed.
10, go for main engine start. We are go for main engine start, T-minus 6, 5, 4, 3, 2, 1, and liftoff of the Space Shuttle Discovery with the Hubble Space Telescope, our window on the universe.
During this mission, Discovery set a new shuttle altitude record. To prevent rapid orbital decay, Hubble had to be released into a near-circular orbit 615 kilometers above the Earth's surface. There were issues with a sticky solar panel, but this was solved and Hubble was released correctly. Technicians monitoring the telescope soon realized that something was awry. Hubble was returning blurred images. Due to misaligned test equipment, the primary mirror had been ground to the wrong curve. However, engineers were able to design corrective optics. 3 years later, the crew of the new shuttle Endeavour would carry out the repair mission. During preparation for the mission, telescope engineers had analyzed the performance of all the instrument's subsystems, looking to make other improvements where possible. Not only would they fit corrective optics, but they replaced the telescope's solar panels and 2 of its malfunctioning gyroscopes. During the 11-day mission, the payload specialists made 5 spacewalks before releasing Hubble.
Right there!
Astronomers waiting on the ground were jubilant.
Get it!
The billion-dollar piece of space junk became the most important observatory in history. Hubble gave us an accurate figure for the expansion of the universe and its age. It revealed distant galaxies in the finest detail, and it allowed us to see the birth of new stars. Its images were stunning. Shuttle missions continued to visit Hubble, carrying out maintenance and replacing old technology with new, giving the orbiting observatory more than 30 years of productive service, and it remains in operation to this day. Yet in the 1990s, one of the shuttle's original goals remained out of reach. Plans for the all-American space station Freedom had been stymied by Washington. But Russia had been operating their own very large space station, Mir, since the mid-80s. With the dissolution of the Soviet Union, NASA began cooperation with Roscosmos, the new Russian Federation space agency. In 1995, the Space Shuttle Discovery made a rendezvous with Mir. NASA wanted to learn about long-duration space missions. And soon, Americans were traveling in Soyuz spacecraft, and Russians were launching on the shuttle. On previous missions, shuttle crews had rehearsed basic assembly techniques. But in 1998, after a new agreement with Russia, the Europeans, and Japan, proper work began on what was now called the International Space Station. What followed was known to shuttle crews as the Wall of EVA, EVA being NASA shorthand for extravehicular activity. NASA had established an EVA office to develop new tools and refine techniques needed for fine assembly tasks. Mission specialists spent months in the training pool, practicing the intricacies associated with their particular mission. In October 2000, 2 Russians and an American launched aboard a Soyuz TM. They took up residence as the first ISS crew, Expedition 1. While they were there, the space station continued to grow as more modules were added. In January 2003, the Space Shuttle Columbia launched on a scientific mission. "15 days later, it re-entered the atmosphere above California.
Columbia, Houston, comm check. Columbia, Houston, UHF, comm check.
Columbia had disintegrated, and all 7 astronauts were lost.
GC plane. Fly GC, lock the doors. Copy.
Examination of ascent footage revealed a piece of insulating foam had parted from the external tank and struck Columbia's left wing. Debris was collected from Columbia's flight path to understand what had happened, but to some at least, the cause had been known since the launch images had been seen. For a second time, the remaining shuttle fleet was grounded. Building work on the International Space Station stopped, and crews had to rely exclusively on Russian spacecraft. Initially, crash investigators suspected workers at the Mishu assembly plant had poorly applied insulation to the external tank. But formal apologies were made when X-ray analysis revealed that thermal expansion and contraction during filling and emptying of the tank led to cracking of the foam. When Discovery finally launched in July 2005, a brace of new safety measures had been introduced, including more detailed recording of the launch, both photographically and with radar. There was a bird strike, which was of little consequence, but more pieces of foam were lost, and though no damage was done to the orbiter, everyone understood that this was just good luck. From now on, shuttles all carried an extension to their robotic arms, which allowed camera inspection of the lower heat shield. Missions would only go to the ISS where a pitch maneuver was performed, enabling additional inspections to be made by the station crew. If needed, the shuttle astronauts could remain on the space station till a rescue mission could be mounted. Between them, the 3 remaining shuttles would make only 22 more flights. And while its days were numbered, some of the most significant work in its 30-year history was made in this time. Using techniques refined over decades, the ISS moved towards completion, with a crew of 6 permanently on orbit. In 2009, dispensation was made for one special last flight to the Hubble Space Telescope. Hubble was in a different orbit from the ISS, so a second shuttle was ready on the ground should the crew need rescue. Again, the telescope was refurbished with up-to-date technology, and its orbit was reboosted. When the space station was completed, the shuttle retired, again leaving the United States reliant upon the Russian Soyuz to carry astronauts to orbit. While it was partially reusable, this didn't lead to the economies that had been envisaged. However, it was big, enabling it to build the International Space Station and to regularly maintain the Hubble Space Telescope. But the shuttle was never able to realize the standard that its designers had promised, and it failed twice catastrophically, killing 14 astronauts. The spacecraft that was to make spaceflight cheap and routine was unsuccessful on both counts. A galaxy cluster from the early universe. This image is based on data from the European Southern Observatory gathered from the Spiderweb galaxy 10 billion light-years distant. All we know about bodies beyond our solar system comes from telescopes. They observe in a range of wavelengths. They're usually located at high altitudes, with some orbiting beyond the atmosphere. Without telescopes, our knowledge of deep space would be negligible. Humanity has always been fascinated with the night sky. Even Stone Age paintings, like this example from the Lascaux Caves in southern France, appears to feature the star cluster Pleiades. For the greater part of history, observers of the stars concluded that the heavens revolved around the Earth. This idea had been formalized by Aristotle, who wrote all heavenly bodies were perfect, and they moved in perfect circles with Earth at their center. In 1543, Copernicus published his seminal work De Revolutionibus, which placed the sun where the Earth had been, explaining the apparent daily motion of the stars by the rotation of the Earth on its axis. Other astronomers were quick to adopt the sun-centered model. It was the dawn of the scientific method. While religious leaders disliked astronomers tinkering with the heavens, they tolerated the idea as a mathematical trick that made it easier to predict planetary positions. It would be decades before this new idea of the universe was confirmed. Yet more astronomers were now willing to break with the ancient Aristotelian view of the sun, the moon, and the planets. But a new tool would be needed to make further progress. In 1609, Galileo built a telescope and trained it on the heavens. Observing the phases of Venus and the orbits of moons around Jupiter were enough to convince him that the Copernican model was reality. He was brought before Pope Urban VIII and spent the rest of his life under house arrest. Galileo's writings were banned by the Pope and remained so for more than 2 centuries. Yet their influence continued spreading across Protestant Europe. As a student, the young Isaac Newton studied the modern ideas from Galileo. In 1668, he designed and built a new type of telescope which used curved mirrors instead of lenses. Newton's analysis of planetary movement built on earlier work by Kepler, who suggested that the planets followed elliptical, not circular paths. In his masterwork, the Principia, Newton set out the laws of motion and devised a new branch of mathematics, calculus, that enabled astronomers to accurately plot planetary motions. Phenomena like eclipses could now be predicted with accuracy. A revolution in astronomy had started with the ever-improving telescope and mathematics, essential tools of observation and understanding. To this day, astronomical telescopes still follow Newton's basic design. In 1919, the 100-inch Hooker telescope was completed. Located on Mount Wilson near Pasadena, the observatory fostered a growing scientific community. A young Edwin Hubble joined the staff at Mount Wilson. At the time, our galaxy, the Milky Way, was regarded as the universe. Distances to planets within the solar system can be calculated via triangulation. While this method can be used to calculate the distance to close stars, for objects thousands of light years away, it simply isn't practical. Hubble, using a new technique that relied on a special type of star known as a Cepheid variable, demonstrated that objects known as nebulae were galaxies at previously unimagined distances. Copernicus had revealed the solar system, and Hubble had revealed the universe. And there was another strange observation. The universe was expanding. In 1948, the Hale 200-inch telescope on Mount Palomar was completed. It enabled discoveries regarding the synthesis of the heavy elements in supernova explosions. Quasars, discovered by radio astronomers, were first seen in visible light at Palomar. Today, we know them as active galactic nuclei, vast clouds of hydrogen spiraling into a black hole. The Hale telescope has been refurbished several times, and it still makes a valuable scientific contribution, but its giant 200-inch mirror is close to the effective limit for this type of instrument. Larger, heavier pieces of glass would sag and distort as they were maneuvered. At the end of World War II, both the Soviet Union and the United States were experimenting with captured German V-2 rockets. For young astrophysicist Lyman Spitzer, this presented new possibilities. Designed as a ballistic missile, the V-2 carried a 1-ton warhead, and it briefly passed above the atmosphere. Spitzer realized the warhead could be replaced by a scientific package, and he called for the construction of an orbiting telescope. To Spitzer, the advantages of such a design were clear, but the idea was decades ahead of the technology that could make it possible. In 1966, NASA began work on a series of small orbiting astronomical telescopes. For the first time, astronomers would be able to make observations at the ultraviolet end of the spectrum. This was one of the great advantages Lyman Spitzer had realized about astronomy from above the atmosphere. Two of the craft failed due to technical issues.
Range ready? Ready. Water system ready? Affirmative.
Significantly, the fourth and final in the series launched in 1973, 500 years after the birth of Copernicus. It was named in honor of the Polish astronomer. The Copernicus Space Telescope discovered several long-period pulsars and it confirmed that the vast clouds of interstellar hydrogen were molecular in form. Engineers learned a lot from building these spacecraft, which informed emerging plans for the large space telescope that Lyman Spitzer was continuing to champion. Budgetary constraints led to a reduction of the mirror size, but a design was finalized by the mid-1970s. Because it required sensitivity deep into the ultraviolet, the large space telescope's primary mirror had to be ground to very fine tolerances. Typical optical telescopes conform to a curve accurate to 1/10 that of the wavelength of visible light. But because of the much shorter wavelengths of ultraviolet, this mirror was made within tolerances 10 times narrower. Specifications stipulated handrails and equipment bay doors, allowing the new telescope to be capable of in-space maintenance. Internal instruments would be modular, allowing them to be swapped out simply. Maintenance missions would regularly visit the telescope, taking advantage of the new Space Shuttle, which would also carry it to its orbit 550 kilometers above the Earth's surface. The servicing missions would give the very expensive space telescope an extended life. As work on the space telescope progressed, astronomers became more excited about the possibilities offered by the new instrument. Its location above the atmosphere would enable 10 times the resolution of the largest ground-based telescopes. Not only does the atmosphere block ultraviolet light, it has a distorting effect upon all images. Twinkling stars in the night sky are direct evidence of this distortion. Work on the Space Telescope had slipped years behind schedule, and the Challenger disaster delayed its launch by several more years. But at last it had been formally named. The Hubble Space Telescope was finally loaded into the cargo bay of the Space Shuttle Discovery. On April the 24th, 1990, it was ready for launch.
Nozzle check of the SRBs. Firing chain is armed. T-minus 6, 5, 4, 3, 2, 1. And liftoff of the Space Shuttle Discovery with the Hubble Space Telescope, our window on the universe.
This flight would set a record for the maximum altitude reached by a shuttle. The day after launch, Discovery's crew were cleared to deploy the telescope.
Good morning, Discovery. You got a go for HST deploy ops.
Hubble is not equipped with thrusters. To point at specific targets, it uses reaction control wheels. Engineers did not want to risk spent fuel contaminating the telescope's precision optics, and it would rely on the shuttle's regular visits to reboost its orbit. Hubble was deployed at an altitude of 614 kilometers. Discovery returned to the ground after a successful mission.
Landing gears down and locked.
But it would be several months before anyone would see results from the telescope that promised to revolutionize astronomy. At the Goddard Space Telescope Operations Center, technicians began a slow and painstaking activation sequence of the Hubble. The first images were disappointing. They lacked the clarity expected of a large aperture telescope above the atmosphere. David Lacrone was Hubble's senior scientist.
It just turned out that there had been a manufacturing error that had left the primary mirror of Hubble, had left it too flat. They took off too much glass. So by just a fraction of the width of a human hair, actually.
The press wrote off Hubble as space junk, and NASA's reputation suffered. Hubble was in orbit and responding correctly to commands from the ground, yet its vision was blurred. NASA had been working on an optical fix for their expensive new space telescope. They understood that it was possible to fit corrective lenses, but there could be no more mistakes. The telescope's subsystems were also scrutinized, and suboptimal items were slated for replacement. Perkin-Elmer, the company that had ground the primary mirror, relied upon a test device that had been incorrectly assembled. The good news was that the error, known as spherical aberration, was consistent. Ball Aerospace was charged with the precision grinding of a series of corrective lenses, housed in a unit that would replace the high-speed photometer.
We had the means now to correct the spherical aberration. And because Hubble could be serviced, this wasn't a problem.
Mission specialists trained extensively in the neutral buoyancy pool. In addition to the optics, gyroscopes would be swapped out, and the solar panels, which had been sending vibrations through the telescope, would also be exchanged.
T-minus 15 seconds.
In December 1993, the repair mission was ready to go.
And we have a go for main engine start. 5, 4, 3, 2, 1. And we have liftoff. Liftoff of the Space Shuttle Endeavour on an ambitious mission to service the Hubble Space Telescope.
It was not until the third day of the mission that Endeavour caught up with Hubble. Just east of Australia, mission specialist Claude Nicollier used the robotic arm to position the telescope in the payload bay. NASA understood the extent and complexity of the work needed for this mission, so 4 astronauts, working in 2 teams, had been assigned for the various refurbishment tasks. During the next 5 days and 5 marathon spacewalks, the mission specialists fitted the telescope's new components, stowing the old parts for return to Earth. While they worked, technicians at the Space Telescope Operations Center monitored Hubble's behavior. As problems arose, they were methodically worked through. A damaged solar panel could not be folded and stowed, so it was discarded to burn up in the atmosphere. The science team who would use Hubble were happy with the way the work had progressed. But it would still be several weeks before the success of the repairs could be confirmed.
Right now, it's looking very, very good that we've accomplished all we needed to accomplish for the optical correction of HST. And that's good news for astronomy. And it's good news for NASA to get over this little episode in our history.
Early in 1994, they finally got to see pictures.
Hey! Right there! Oh!
They were not disappointed. Hubble was now delivering images from deep space of unprecedented clarity. The higher resolution immediately led to the realization that some stars that had been observed for decades were in fact double stars orbiting a common center of mass. When Edwin Hubble used the Hooker telescope to determine that the universe was expanding, he observed redshift, the shift of absorption lines toward the red end of the spectrum of light from distant galaxies. This happens as an object moves away from its observer. The more distant the galaxy, the greater the redshift. This relationship became known as Hubble's law. He used the most advanced technologies of his day. Now, the telescope named in honor of Edwin Hubble was capable of refining his estimates to a much higher degree of precision. Astrophysicists wanted to pin down the Hubble constant, the rate at which the universe continues to expand. One theory suggested that the attractive force of gravity would be slowing down the expansion, and several groups thought they had a way of finding out. They understood that a particular type of supernova explosion, a type 1A supernova, had a predictable brightness. Accurately recording the brightness of very distant Type 1a supernovae would give another clue to their distance. Differences between redshift information and apparent brightness would suggest a change in the rate of expansion. Using ground-based telescopes to find and track changes in brightness of this special type of supernova was extremely difficult. The clarity of images from the Hubble telescope would make this task easier, but scientific peers of these supernova hunters suggested that cosmic dust could reduce the brightness of objects at such great distances. The groups had too few examples to show plausible results, so an accurate figure for the expansion of the universe would have to wait for time on the newly refurbished Hubble. As much as 10% of observational time on Hubble is allocated at the discretion of the Space Telescope's director. In 1995, it was decided to push the Hubble to its limits. They wanted to see into the farthest reaches of the universe. The exercise was known as the Deep Field. Whatever was at the extreme distances they wanted to probe would be very dim, so the telescope would make a time exposure lasting more than 10 days. A target region was selected that was clear of bright local stars.
One of the neat things about the Deep Field, they picked a spot where there wasn't anything. They looked and they said, there's absolutely nothing here.
Some astronomers felt that looking at a patch of empty sky for 10 days was a waste of valuable observation time, and it was a technically difficult assignment.
There's an exposure time that's expressed, I think it's 11.2 days, but probably what's more important is how many orbits it took us to do that. 400 orbits of Hubble data to take that image.
Hubble revealed that the blank area of sky was not empty at all.
We see some of the faintest objects showing up in these images, and those faint objects are often distant galaxies. These deep fields have revealed visually to us a universe absolutely teeming with galaxies, hundreds of billions of galaxies. In one deep field alone, we can see 1,000 of these little smudges of light, which are distant galaxies. By doing that, we can compare galaxies that are shining to us from billions of light years away with galaxies closer to us, or even to our own Milky Way, and see if they're similar or different. What Hubble has revealed is that the universe has in fact changed over these billions of years of time.
It's an investigation that Hubble has repeated throughout its life, particularly after each upgrade. To repeatedly find the exact area in the sky for the multiple exposures required for the deep field investigations, Hubble's fine guidance system can point the telescope with an accuracy better than 2 millionths of 1 degree. Three fine guidance sensors can lock onto guide stars, and 6 rate gyro assemblies are used to determine the rate and direction of any drift. Both systems send information to the guidance computer that generates corrective instructions for the 4 heavy reaction control wheels. As a wheel rotates, the telescope will move in the opposite direction. Combined movement of the 4 angled wheels can point the telescope with extreme precision. Because they have moving parts and are subject to wear, the reaction control assemblies are modular and designed to be easily replaced. One assembly was replaced during the second servicing mission in 1997. At the same time, the observatory received a new solid-state data recorder and a near-infrared camera that gave the telescope greater reach. After the 10-day refurbishment, Hubble was set free, essentially a new telescope. And it had a new capability. Its near-infrared camera could see light that was not blocked by interstellar gas and dust. This was important for the teams trying to get an accurate figure for the expansion rate of the universe. they had divided into two multinational groups: the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt. Essentially, they followed similar methodology, with most of their work being done using ground-based telescopes. Yet it took observations from the Hubble Space Telescope to dispel doubts about dust possibly skewing their data. However, both groups hesitated in publishing their results because they were not what anybody had expected. The expansion of the universe was speeding up, driven by a mysterious force, dark energy. The result was so significant, it led to the Nobel Prize for Physics.
Professor Saul Perlmutter, Professor Brian Schmidt, Professor Adam Rees. You have been awarded the Nobel Prize in Physics for the discovery of the accelerating expansion of the universe.
It was one of those discoveries that answers one question, but raises many others. Nobody really understands dark energy or dark matter, and cosmologists are bemused that what we see makes up only 4% of the universe. Hubble's technical advances would help astronomers across a number of areas, but during the 1990s there were design advances made in terrestrial telescopes too. The limiting factor in telescopes had always been mirror size, but in 1989 the European Southern Observatory completed the New Technology Telescope, which had a very thin 3.6-meter mirror. Its designers addressed the issue of distortion with computer-controlled actuators that flex the thin mirror to preserve the accuracy of its curve. Known as active optics, this technology has been adopted by all modern observatories. In the mid-1990s, the twin Keck telescopes on Mauna Kea in Hawaii saw first light. Each has a 10-meter primary mirror made up of 36 hexagonal segments. Through the use of active optics, actuators positioned behind the segments enable them to act as a single mirror. The Keck Observatory introduced a laser system that enables each telescope to monitor atmospheric turbulence and dynamically readjust its mirrors to compensate for the atmospheric distortion. Again, this technique, known as adaptive optics, has been adopted around the world. NASA engineers were aware of these developments, particularly the segmented optics, and they made plans for the next-generation space telescope with a set of hexagonal mirrors that could be folded up during launch to be unfurled in space. Hubble was still returning outstanding scientific results, and it would be decades before it could be replaced. To keep public and political engagement, NASA made sure that batches of its more spectacular images were released regularly.
Here at the -V2 side of the Hubble Space Telescope. Of course,
NASA was planning to make a third upgrade mission to Hubble in mid-2000. A meticulous plan had been established, and work routines were being practiced when, in April 1999, the third of Hubble's 6 gyroscopes died. The telescope could still function perfectly on the remaining 3, but any further gyro malfunctions would disable it. NASA split the servicing mission into 2 parts, scheduling Part A for November 1999, when they would replace all the gyros. As Discovery's launch neared, a 4th gyro died, and Hubble went into safe mode. It could not operate until the repair mission had been completed. Problems with wiring, with an engine and a misshapen fuel line, as well as weather issues, all contributed to 9 postponements of Discovery's servicing mission.
3,
2, 1. Ignition and liftoff. Discovery now on its way to service NASA's Hubble Space Telescope.
Late in December 1999, Discovery launched successfully. After 30 orbits, the shuttle caught up with the Space Telescope and positioned it in a support cradle at the rear of the cargo bay. Mission specialists replaced Hubble's 3 rate sensor units. Each of these contained 2 gyroscopes. During 2 subsequent spacewalks, the astronauts replaced Hubble's original computer with a far more powerful unit, and the 2 remaining reel-to-reel data recorders were replaced with a solid-state recorder. The original flight schedule called for a 10-day mission.
Landing gear down.
But this was shortened to 8 days to avoid the calendar change to the year 2000.
Touchdown.
Flight planners were nervous about some ground support computers being upset by the Y2K bug. The mission was a success, but the second part of Hubble's maintenance had to wait 14 more months. Yet, even as the Space Telescope was completely renewed, engineers were planning the next servicing flight. Scheduled for late 2005, the mission would introduce the very latest technology to equip Hubble with abilities that were not contemplated when it was originally built. In 2003, a new Space Telescope was being prepared for launch. While its 85-centimeter mirror was much smaller than Hubble's, it was sensitive deep into the infrared end of the spectrum. There had been 2 previous infrared space telescopes, but they had very limited time in space, and infrared detectors had advanced dramatically since these earlier missions. Till launch, it was known as Certif. When it was successfully positioned in its Earth-following orbit around the Sun, it was renamed the Spitzer Space Telescope, in honor of Lyman Spitzer, the man who championed space-based observatories. Spitzer carried 360 liters of liquid helium to cool its infrared detector to near absolute zero. It was able to penetrate vast dust clouds, revealing very faint, very distant stars, transforming astronomers' ideas about very familiar bodies. Soon, astronomers from the University of Texas at Austin used Spitzer to locate a faint glow in a cloud of gas and dust. It's thought to be a young star in its earliest stages of development. In 1999, during a survey of relatively close stars, a red dwarf, slightly larger than Jupiter, was discovered in the Aquarius constellation. It's an old star, 3 billion years older than our Sun. It was given the name 2-mass J230629228-0502285. Not a very catchy title, but it was of great interest. Astronomers were looking for exoplanets, planets orbiting stars outside our own solar system. And this particular star was small enough to dim significantly should it have a planet that crossed its face. A remotely controlled telescope, part of the European Southern Observatory, was built to look for exoplanets. By monitoring the brightness of a star, it could infer the presence of an orbiting planet. The telescope is known as TRAPPIST-South, a contraction of Transiting Planets and Planetesimal Small Telescope. When it examined the red dwarf, variations in the light suggested there were 2 planets around the star. Thankfully, it was renamed TRAPPIST-1 after the observatory, and telescopes around the world were turned to TRAPPIST-1. Spitzer's sensitivity in the infrared made it ideal for this type of search, although its designers had no idea this could be one of its uses. Soon, Spitzer discovered 5 more planets orbiting in the TRAPPIST system, and scientists became very excited. Most of the planets were similar to Earth in size. Ultimately, Hubble was focused on the TRAPPIST system to examine the planet's atmospheres. This was the first time spectrographic analysis of an exoplanet had ever been made. Results suggested that the type of heavy, hydrogen-rich atmosphere found on the giant gas planets was not present. More evidence that at least some of the TRAPPIST planets had a rocky surface, like the Earth. It is now thought that most stars have some form of planetary system, and the search for exoplanets is a growing branch of astronomy.
Columbia Houston, com check.
February the 1st, 2003.
Columbia Houston.
The Space Shuttle Columbia breaks up while re-entering the atmosphere. All crew die. Shuttle flights are suspended pending an inquiry and a redesign of faulty components. All future flights will be limited to the International Space Station, where the crew of a damaged shuttle could await rescue. Upon completion of the space station, the shuttle fleet will be retired. There will be no more servicing missions to the Hubble Space Telescope. Hubble's orbit, shown in blue, is at a different inclination to that of the International Space Station, shown in red. With only limited maneuvering fuel, it would be impossible for the shuttle to change to the ISS's steeper orbit. Across the United States and in the corridors of power, this was not a popular decision. Over more than a decade in operation, Hubble discoveries prompted the rewriting of textbooks, and its steady stream of beautiful images had convinced everybody that the orbiting telescope was worth supporting. Michael Griffin became NASA chief in June 2005. After the shuttle's successful resumption of service, he made an important announcement.
We are going to add a shuttle servicing mission to the Hubble Space Telescope to the shuttle's manifest to be flown before it retires.
It was a popular decision, but mission planners had no time to waste. Even though the servicing mission would not fly for another 2.5 years, replacement parts had to be built, the procedures had to be devised, and the crew had to be thoroughly trained. A new, more powerful camera and a new UV spectrograph would be installed. The Space Telescope imaging spectrograph had failed, and its power supply would be repaired in space. Nothing like this had previously been attempted, and a new suite of tools was designed for the task. For each hour spent performing a particular task in space, at least 10 hours were spent in the neutral buoyancy pool rehearsing. Everyone understood that this was the last time Hubble would be serviced, so all measures were taken to extend the telescope's useful life as much as possible. Critical systems, the gyros, the computer, and the batteries were all to be replaced. In 2007, things became more complicated. The advanced camera for surveys went black. Its power supply had also failed. It was Hubble's most frequently used instrument. Without it, the telescope was half blind. The 11th of May, 2009.
T-minus 10, 9, 8, 7, 6, 4, 3, 2, 1, and liftoff of Space Shuttle Atlantis. Final visit to enhance the vision of Hubble into the deepest grandeur of our universe.
It was fitting that the final servicing mission to Hubble should be the most ambitious. Over 5 spacewalks, all objectives were achieved, though there were difficulties. A bolt was stuck, and one of the replacement rate-sensing units refused to fit into its slot.
Looks good.
In NASA fashion, these problems were solved. Brute force shifted the bolt, and a spare rate-sensing unit did fit.
You want the cutters now or down at the mink?
Again, Hubble was released with capacities beyond its original design.
Motion is stop, Scooter.
Okay, here comes the burn. 10 down pulses. Mark.
At the base of the telescope, the astronauts had fitted a capture ring. At the end of its life, a robotic spacecraft will grab the telescope and nudge it toward Earth, where it will burn up.
That's 10.
Okay,
Flight controller's
1857
off.
point. Okay, I need the mic.
There could be no more servicing missions because soon there would be no more space shuttles. While Hubble continued making valuable contributions to astronomy, the science community began to focus on its successor. The next generation space telescope had now been renamed James Webb after NASA's Apollo-era administrator. Construction of the new space telescope was underway in the early 2000s, with a launch date set for 2010. As work progressed, it became obvious that this was overly optimistic, and the schedule continued to be pushed into the future. Compared to Hubble, it is huge, yet it's only half Hubble's weight. Astrophysicists wanted to see deeper and further back in time to the earliest days of the universe, and so Webb was designed with sensitivity into the very low end of the infrared spectrum. What makes the Webb telescope so special are its 18 hexagonal mirrors. They are made from strong yet light beryllium and are coated with a thin layer of gold with a very fine overlay of glass. They align to work as one giant mirror 6.5 meters in diameter. To observe in the mid-infrared, Webb is kept at temperatures below 50 degrees Kelvin. That's around minus 223 degrees Celsius. To help achieve this, most of the telescope is shielded from the sun by 5 layers of kapton. The telescope's mid-infrared detector, known as MIRI, must not exceed 6 degrees Kelvin and is refrigerated by a helium gas cooler. The fully deployed telescope could not be accommodated by any rocket, so it had to be folded to fit inside the payload stage of an Ariane 5. As part of its contribution to the multinational nature of the Webb telescope, the European Space Agency was bearing the cost of the launch from French Guiana. However, before it could be launched, it had to undergo a range of tests. Its size meant that it could not be tested as a whole unit. Components were tested separately.
What we're going to do now is shake it, blast sound at it, heat it, cool it, and make sure that everything is working exactly like it should.
The telescope had to be optically tested in a vacuum at the low temperatures needed for its operation in space. During the 1960s, NASA had built Chamber A for work on the Apollo program. It is the largest vacuum chamber in the world, and it had been extensively modified for its work with Webb. It was thoroughly cleaned, and a helium shroud was installed to achieve the extremely low temperatures. After the door was sealed, it took close to a week to evacuate the chamber and a further 30 days to bring everything inside down to 40 degrees Kelvin. Chamber A had been fitted with optical test equipment so engineers could align individual segments to perform as a single mirror. They also validated the functioning of Webb's 4 instruments. Everything performed as intended, and by late September 2017, the team began allowing the telescope to return to room temperature. After 93 days, the door was reopened, and the telescope element began preparation for its next test. In California, the sunshield was tested and retested. Critics said there were too many single failure points in the Webb telescope, and the sunshield was an especially worrying system with 5 layers of fragile kapton that had to unfold flawlessly. In August 2019, all pieces of the James Webb Space Telescope finally came together, 12 years behind schedule. Recommendations made by an independent review board that had to be implemented, and the COVID pandemic pushed the launch date out by a further 2 years. In September 2021, the telescope was trucked through the late-night streets of Los Angeles. NASA had given no notification about this move because it felt such an expensive cargo might attract the wrong type of attention. Webb, in its air-conditioned container, with the truck that hauled it, was loaded into a French ship for its journey to the launch site. "14 days later, it arrived at Kourou. From this point, it was effectively in European hands. At the launch center, Webb was readied for fueling. Unlike Hubble, the Webb telescope has thrusters for mid-course corrections and for station keeping. Technicians need protective suits because the hypergolic fuel is highly toxic. The fuel is a scarce resource that will limit the telescope's life. It was hoped that, with careful use, this fuel would last for 10 years. At the same time, the Ariane 5 was being assembled. The Webb telescope was to be the most expensive payload any rocket had ever lifted. The last piece to join the stack was Webb itself. This Ariane 5 had been customized for the JWST's unique needs. The fairing that protected it during its ascent had to have extra venting ports. Any difference in pressure as the fairing was discarded could damage the fragile sunshield. And because clearance between Webb and the fairing was so narrow, special laser guidance devices had been devised to ensure a perfect fit. There was just enough room to allow for the telescope's expected movement within the fairing during launch. It had taken 2 months to complete the launch preparations and a further 3 decades to design and build the James Webb Space Telescope.
7, 6, 5.
Finally, on Christmas Day in 2022, it was ready.
Stop. Allumage Vulcain. Allumage UAP. Décollage.
A launcher is programmed to send its spacecraft accurately on the specified trajectory, but this does not always happen with precision. To compensate for inaccuracies, the flight plan had scheduled 3 course correction maneuvers that Webb would make during the cruise phase. Webb was headed for the second Sun-Earth Lagrangian point, where the Sun and the Earth's gravitation are in balance. 1.5 million kilometers distant, the Space Telescope receives almost no heat from the Earth or the Moon. The spacecraft adopted a halo orbit around L2, requiring very little propellant to maintain a stable position. Webb is designed to function at extremely low temperatures, and until it could deploy its sunshield, it was vulnerable to solar damage. To minimize intense heating to any individual parts of the telescope, the Ariane's upper stage made a series of rolling oscillations. Usually, the launch is the most difficult part of any space mission, But during the month that it took Webb to reach the L2 point, it had to carry out the most complex deployment any spacecraft had had to handle. Its designers knew that during deployment, there were 344 single points where a failure would render the Webb telescope useless. The solar panel, and soon after the high-gain antenna, were the first to unfold. They were the only components to deploy automatically. Then came the first course correction maneuver. So accurate was the launch that the mid-course corrections were far smaller than expected. This doubled the amount of fuel left for station keeping, effectively adding a further 10 years to the telescope's life. From then, all other deployments were initiated by command from the ground and closely monitored. It took 14 days for all the pieces to unfold into their operational positions, yet the telescope had not reached the L2 point, nor had it cooled to its operating temperature. After unfurling the sun shield, Webb was adjusting to its operational mode, with a hot side featuring the solar panel, the communications dish, and the thrusters, and a cold side with all the optical components and data processing safely protected from the sun. After cooling, the slow process of precisely aligning the mirrors began. At a distance of 1.5 million kilometers, engineers at the Space Telescope Science Institute began microscopic adjustments to the 18 mirror segments. This took a further 6 months. Only then was the Webb Space Telescope ready to begin its scientific work. The scientific community understood that the technical advances in Webb's design were so great that they could expect surprises. Familiar bodies were revealed in a completely new way. While Hubble was a breakthrough for astronomy, it made astrophysicists realize that to see the most distant galaxies required superior ability in the low end of the spectrum. In ways that were previously not possible, the James Webb Space Telescope has begun investigating the earliest galaxies in the universe, the formation of stars, and even planets in our close neighborhood. And it's already delivered surprises. When the JWST made its first deep field survey, it identified the oldest galaxy yet observed, seen as it was when the universe was just 3% of its current age. Webb is expected to continue in active service for around 25 years. And already information gathered by the telescope has scientists rethinking ideas about the universe. The Sun is just one of 100,000 million stars in our galaxy. It makes up 99% of the solar system's mass, and its gravitation holds all the planets in their orbits. The Sun is a giant nuclear furnace that bathes the planets in warmth and light. Life on Earth depends on this energy. The Sun's immense gravity squeezes hydrogen atoms together to form helium, liberating vast amounts of energy. The high temperatures rip electrons from their atoms, resulting in highly charged plasma, the fourth state of matter. Its surface is a tangle of surging magnetic fields, regularly ejecting gigantic clouds of charged particles. If they collide with Earth, the effects can be drastic. Power supplies can be overwhelmed. Spacecraft have been knocked out of orbit, and communications systems relying on satellite relays have gone black. There are fundamental questions about the sun's behavior that modern science is making great efforts to answer. Scientific studies of the sun started in the early 17th century, when Galileo turned his telescope to the heavens. Various observers began documenting sunspots' movement across the solar disk. In the 19th century, after gathering data for 25 years, Heinrich Schwabe noted a regular pattern of sunspot activity that followed an 11-year solar cycle. During this cycle, the sun shows very little sunspot activity at solar minimum, on the left, when solar storms are infrequent. At solar max, on the right, sunspots proliferate and giant solar flares are common. When astronomers learned to predict eclipses, a new type of solar investigation opened. With the sun obscured by the moon, it became clear that it was surrounded by a vast and intricately patterned aura that became known as the corona. Using a spectrograph, British astronomer Norman Lockyer analysed the inner corona. He saw a previously unknown element. It became known as helium, from the Greek helios, the sun. As electrical technologies like telegraphy became common, new phenomena were noticed. In 1859, English astronomers Richard Carrington and Richard Hodgson recorded a solar flare. While observing a group of solar spots on the 1st of September, I was suddenly surprised at the appearance of a very brilliant star of light, much brighter than the sun's surface. Richard Hodgson. At the same time, magnetometers at the Kew Observatory recorded strong magnetic activity. That night, auroras stretching from the poles to the tropics were seen, and telegraph operators around the world reported sparking wires and electric shocks. While Carrington and Hodgson accurately recorded their observations, they were reluctant to link auroras to solar activity. Modern science accepts that what is now called the Carrington event was the greatest coronal mass ejection to hit the Earth in modern history. Early in the 20th century, Norwegian physicist Christian Birkeland observed that an electron beam directed toward a spherical magnet produced rings of light around the poles. He proposed that rays of electric corpuscles from the sun could impinge upon the Earth's poles in the same manner, resulting in auroras, but his theory was disregarded. Space-based science began in 1946, when the United States, using captured V-2 rockets, made ultraviolet observations of the sun. Most UV cannot be observed from the ground because it is blocked by atmospheric ozone and oxygen. The work continued over a series of flights, eventually leading to spectral evidence of highly charged iron in the solar corona. Only extreme temperatures, millions of degrees Kelvin, could account for the results. This means the sun's varying corona is around 200 times hotter than its surface. How could this be? In 1963, a research satellite, Transit 5E1, was launched in tandem with an early navigation satellite. Transit 5E1 went into a polar orbit to study charged particles, magnetic fields, and solar spectra. Detailed analysis of the data returned by Transit 5E1 showed a clear link between charged particles above the poles, solar activity, and auroras. Proof that Birkeland's theory was correct. Today, we understand that auroras are caused by protons, electrons, and alpha particles with traces of heavier ions ejected from the sun. Most are deflected by the Earth's magnetic field, but some spiral into the atmosphere along the Earth's magnetic field lines. The particles interact with oxygen and nitrogen in the upper atmosphere. At times of heavy solar activity, auroras can stretch further north or south from the poles. While nuclear physics had revealed how the sun, as a giant fusion reactor, converted matter into energy, there were very puzzling questions about its behavior. In the 1950s, American physicist Eugene Parker proposed a theory suggesting that a constant stream of ions flowed from the sun. It was called the solar wind. And again, the idea was largely ignored. But this was the space age, and soon spacecraft from the Soviet Union, as well as the US Mariner 2 mission, began detecting the solar wind. The theory became fact, and Eugene Parker continued to play an important role in heliophysics well into the 21st century. As space technology grew more complex, with increasing reliance on satellite communications, research missions began observing the sun more closely, and a new term, space weather, entered the lexicon. Space weather can result in increased atmospheric drag on low-orbiting satellites. It can push geosynchronous satellites out of position, and clouds of plasma can even kill satellites. In 1973, at the end of NASA's Apollo program, a highly modified Saturn V was prepared for a very different mission. Skylab was to be the United States' only independently operated space station. The rocket's upper stage would not be used for propulsion. It had been equipped as an orbital laboratory.
11, 10, 9, 8. We have ignition sequence has started. 6, 5, 4, 3, 0. And we have a liftoff. The Skylab lifting off the pad now, moving up. Skylab has cleared the tower.
One of its major tasks was to serve as a solar observatory. The images it captured and the scientific return represented a breakthrough in solar physics. Skylab pushed 1970s technology to the limits. A cluster of 6 telescopes recorded solar behavior in various ultraviolet and X-ray parts of the spectrum not visible through the Earth's atmosphere. The telescope cluster, originally intended to be mounted on an Apollo spacecraft, could not be reached from within the laboratory. Yet the images from all but one of these instruments had to be recorded on film. This required the crew to leave the Skylab periodically to exchange the film canisters. Earthbound astronomers were initially skeptical of the solar observations that Skylab was asked to do. But as the exposed film returned to the ground, they realized that both the quantity and quality of the data would keep analysts busy for years. Skylab delivered the first images of solar flares, and holes in the corona and X-ray bright points were also discovered. Film was still the primary recording medium because it offered far greater resolution than the slow-scan television systems available at the time. But film had to be returned to Earth to be processed and viewed. While this was feasible with orbiting missions like Skylab, engineers realized that they would have to devise a high-definition system for deep space missions that could not return to Earth. Since the 1600s, astronomers have made estimates of the sun's rotation by tracking sunspots. But the sun is not solid, and at high latitudes, the spin rate is different. Viewed from the Earth, our star's equator spins once every 25.5 days and once every 33.5 days at 75 degrees latitude. All the planets in our solar system orbit in the same direction as the sun's rotation and roughly in the same plane, the ecliptic, as the sun's equator. This means we cannot see the sun's polar regions from the Earth. In 1990, a joint mission between NASA and the European Space Agency was launched from the Space Shuttle Discovery. Called Ulysses, it first traveled to Jupiter to use the giant planet's gravity to loop beneath the ecliptic and back toward the sun. This would give Ulysses the opportunity to gather solar data from every possible angle, including the poles. Over a 17-year period, more than one complete solar cycle, Ulysses orbited the sun 3 times and discovered that its magnetic field flips every cycle, and it observed the solar wind from the poles traveled faster than that from the equatorial regions.
3, 2, 1, ignition. And liftoff of Soho and the Atlas.
In 1995, another ESA-NASA joint mission launched. The Solar and Heliophysics Observatory was put into orbit around the first Earth-Sun Lagrangian point. Among its 12 instruments were a coronagraph and a unit called GOLF, from global oscillations at low frequencies. The coronagraph is a telescope with an inbuilt disk that masks the sun to enable detailed observations of the corona. Barely 2 years into its operations, 2 of SOHO's 3 gyroscopes failed and the craft began tumbling. It took months to reacquire a signal and then slowly regain control. SOHO's operational software was rewritten to allow it to function without gyros. Since then, SOHO has functioned flawlessly, and its contributions have been significant. The probe's GOLF instrument has measured vibrations from the sun, similar to quakes on Earth, allowing scientists to picture the solar core. It spins roughly 4 times faster than the rest of the sun. The probe made breakthroughs in our ability to see writhing magnetic features like giant looping flares and solar tornadoes. For the first time, it was possible to see clearly coronal mass ejections that can bombard the Earth. Early detection allows vulnerable technologies time to prepare. The sun is a vast tangle of magnetic field lines that affects the whole solar system. We are fortunate that our planet has its own magnetic field. Convection within the Earth's iron-rich core gives our world a magnetic shield that protects us from the worst extremes of solar storms. Solar field lines can connect with the Earth's field lines, conducting vast amounts of charged particles into the geomagnetic system. When the connection breaks, the particles blast into the upper atmosphere, and we see auroras like these viewed from the International Space Station. Because of our reliance upon technologies that are vulnerable to these high-energy particles, NASA built a suite of satellites to learn about the complex magnetic interactions taking place around the Earth, particularly during heavy solar activity.
0.
And liftoff of the Atlas V with MMS using magnetic reconnection.
The Magnetospheric Multiscale Mission, or MMS, was launched in 2015. The 4 spacecraft gradually separated. Then each deployed a series of radial and axial booms, enabling them to measure hot plasma, energetic particles, and both magnetic and electric fields. The probes dispersed into a tetrahedral formation using GPS signals from the ground to lock into position. This allowed them to accurately map, in 3 dimensions, the electromagnetic activity at the boundary of the Earth's magnetic field. The MMS probes were the first to directly register reconnection events. They are helping us understand the transfer of energy at reconnection and the acceleration of particles. The MMS probes are expected to continue in service until 2040. A similar mission is soon to go to Mars. Our neighboring planet has very little atmosphere and a very weak magnetic field. Water once flowed on its surface. NASA's ESCAPADE mission will find out what role the solar wind could have had in stripping away the Martian atmosphere. Sunspots are more frequent during periods in the solar cycle of great activity. These are the times when huge ejections of coronal material can sweep toward the Earth, with major consequences for communications, navigation, and electrical power grids. While there are techniques to predict developments on the far side of the Sun, they are inaccurate. A pair of solar satellites observing the Sun from different angles could monitor solar activity everywhere. The 2 stereo probes were launched in 2006. They separated and initially headed toward the Moon. Arriving at different times, they used the lunar gravitation to further separate along a sun-centered orbit. Their positions continued to diverge, ultimately allowing a combined view of the complete Sun. Each spacecraft is fitted with cameras, particle experiments, and radio detectors. Their microprocessors are radiation hardened to resist extremes of the solar environment. 2 differing aspects of solar storms were of interest to the stereo team. Coronal mass ejections, here seen from Stereo A's coronagraph, happen when magnetic field lines break, blasting billions of tons of solar plasma from the corona out into space. If it's on a collision course with Earth, it will take between 1 and 3 days to arrive. Solar flares are bright eruptions from the Sun's surface. Brilliant light, including X-rays, will take just 8 minutes to reach the Earth. Data from the stereo satellites improved the accuracy of space weather alerts. In 2012, Stereo A passed through a coronal mass ejection of similar strength to the Carrington event. It survived unscathed and relayed valuable information. In October 2012, NASA lost contact with Stereo B. Subsequent analysis discovered the craft was in a rapid spin. Numerous attempts were made to re-establish control, but after 3 years, recovery operations were abandoned. Stereo A continues in operation. Its off-axis view complements other solar observing satellites. In the year 2000, the still incomplete International Space Station received its first permanent crew. While they orbit well below the Van Allen belts, without the protection of a deep atmosphere, the crew members will still experience higher doses of radiation than people on the ground. Solar storms can further increase the risk to astronauts, so solid information on the sun's behavior became even more important. The following year, NASA established the Living with a Star program. This new program coordinated international solar research with an emphasis on the sun's effect upon the Earth, its people, and its modern technology. Just as meteorologists observe weather patterns around the clock, a new space weather service would continually monitor the sun. Soon, at NASA Goddard in the clean room in Building 29, the first in a new generation of solar monitoring satellites was taking shape as the foundation stone of the Living with a Star program. The new satellite was to be known as the Solar Dynamics Observatory. It was designed so solar physicists could understand solar processes with a view to predicting the behavior of the sun. It had to monitor the complete disk of the sun continuously, and it had to capture high-definition pictures in 10 different wavelengths. The amount of data SDO would generate was huge. No flight-tested recorder could handle the load, so the satellite would have to remain in constant contact with a ground station. A dedicated receiving facility with 2 18-meter antennas was built at White Sands, New Mexico.
4, go for main engine start. 3, 2, 1, 0. And ignition and liftoff of the Atlas V with the Solar Dynamics Observatory, learning why our star is changing our lives.
It was launched in February 2010. SDO is in a circular geosynchronous orbit inclined at 28 degrees, about the longitude of the New Mexico receiver. It can almost always see the sun while remaining in contact with the ground. Each day above the White Sands facility, it appears to move in a figure of 8. The satellite's atmospheric imaging assembly consists of 4 adjacent telescopes capable of viewing the sun in 10 different regions of the electromagnetic spectrum. In visible light, we can see the surface, the photosphere, at around 5,800 degrees Kelvin. Here we can observe sunspots. Moving up through the inner layers of the corona, the temperatures increase drastically, and the light emitted climbs higher into the ultraviolet, with different features being revealed. By convention, different colors are used to represent the different parts of the extreme ultraviolet spectrum. The 304 angstrom wavelength highlights the transition region from the photosphere to the chromosphere. It is particularly good for observing flares and prominences. The same event, viewed at different wavelengths, reveals different features. Ordinary lenses are opaque to these high-energy wavelengths, so designers employed curved mirrors to focus extreme ultraviolet light onto the camera's sensors. Not only was the SDO designed to capture high-definition images across the high-energy spectrum, it had to do so at a rapid cadence and over extremely long periods of time. The ground station must receive a downlink rate of 130 megabits per second for months. The data is relayed to several science operations centers, from where it is made freely available to services and researchers around the world. The data flow from the SDO and its rapid dissemination revolutionized solar research and space weather alerts. The US's National Oceanic and Atmospheric Administration operates the Space Weather Prediction Center. Its daily bulletins are important for power infrastructure, communications, and GPS services. If the International Space Station is threatened by a coronal mass ejection, the occupants will shelter in the Russian Zvezda module, the most heavily shielded part of the space station, and non-essential electronic equipment will be switched off. If the approaching radiation appears severe, the crew can rapidly return to Earth in the attached Soyuz or Dragon capsules. So far, this has not happened. Researchers are looking for patterns of solar behavior that might lead to the development of predictive modeling. Almost continuous observation allows statistical analysis of solar events. There is a link between the dimming of the corona and coronal mass ejections, and solar flares are often followed by a secondary late-phase flare. The information is building an important research archive. Yet, heliophysicists digging into sunspot records that have been collected over centuries understand that our star's behavior varies greatly over longer periods. While we speak of a solar cycle of 11 years, it has sometimes been as short as 8 years or as long as 13 years. Researchers think this variation fits into an even longer 80 to 90-year pattern. There appears to be a strong correlation between a sparsity of sunspots, solar dimming, and long-term temperatures on Earth. In 1976, a paper written by astronomer John A. Eddy built upon work from 19th century researchers Gustav Spörer and Edward Maunder. They had identified a period of remarkably little sunspot activity that coincided with a prolonged cold period known as the Little Ice Age, where the Thames in London would regularly freeze over. Tree ring analysis backed this up and suggested a similar period had bridged the 13th and 14th centuries. Realizing this led to new questions about the influence that the sun has on planet Earth's climate. In 1958, the United States' first satellite, Explorer 1, was launched. It was equipped with a modified Geiger counter. Researchers had hoped to detect cosmic rays, high-energy particles from deep space. The instrument registered radiation levels 1,000 times greater than expected. James Van Allen, who had designed the experiment, realized that 2 layers of high-energy particles encircled the Earth, and in 1958 they were named the Van Allen radiation belts. They are areas of highly charged particles from the sun, trapped by the Earth's magnetic field. In 2012, the Van Allen probes were launched, also as part of NASA's Living with a Star program.
Lift off the Atlas V rocket and twin spacecraft on a mission to unlock the mysteries of Earth's Van Allen belts.
Clearly, what happened at the sun was only part of the Sun-Earth interaction. The Van Allen belts vary in size and intensity according to solar activity, but this process is not well understood. Most satellites switch to safe mode when radiation levels become critical, shutting down, waiting to be restarted by a signal from the ground. But these are just the conditions that the Van Allen probes were designed to monitor. Their circuitry was radiation hardened and protected by thick metallic shielding. Their highly elliptical orbit had them passing through every level of the inner and outer radiation belts. Although great care had been taken to ensure they could function in this hostile environment, they were only expected to last for 2 years. Launched near the peak of a solar cycle, The two probes promptly returned data revealing the extent of the outer and inner belts, but within days a wave of solar particles swept past the Earth and a new middle ring emerged. Scientists were scratching their heads about the extra radiation belt when another, even larger coronal mass ejection hit, wiping away the outer and middle belts. A week later, yet another cloud of particles hit, restoring the original inner and outer rings. It was thought that the high-energy electrons that had suddenly disappeared had entered the atmosphere. A series of high-altitude balloon flights, launched from both the southern and northern polar regions, was made to detect high-speed electrons entering the upper atmosphere. They were timed with the overflight of the Van Allen probes. The missions detected a rain of energetic electrons entering the upper atmosphere as electrons disappeared from the radiation belts. The Van Allen probes went on to map variations in the electrical complexities of the near-Earth regions for 7 years, far beyond the satellite's expected lifespan. Key questions remain unanswered. How is the surface temperature of the Sun around 6,000 degrees Kelvin, when the corona, the Sun's atmosphere, is between 1 and 2 million degrees Kelvin? And the outflow of solar plasma, we call the solar wind, is accelerated to incredible speed. How? Since the discovery of the solar wind, people like Eugene Parker had called for a probe to be sent into the solar corona. But only recently has the technology caught up to the scientific ambition. Late in 2010, engineers at the Johns Hopkins Applied Physics Lab began work on what NASA refers to as the most autonomous probe ever built. The Solar Probe Plus would have to look after itself for large portions of its mission while it was near the Sun and out of contact with the Earth. The craft was designed to shelter from the intense radiant heat behind a carbon-carbon heat shield, and water would flow through the stubby tips of its solar panels to provide cooling. A year before it was due to launch, Eugene Parker, who predicted the existence of the solar wind, received a phone call.
They've been working on the spacecraft for several years, and one day the phone rang, and a guy that I know said, "We're talking about putting your name on the Solar Probe Plus," it was called. And did I object? And I sort of said, "No, I feel rather flattered." So he said, "Okay, that's what we'll do."
The Parker Solar Probe is the first NASA spacecraft to be named after a living person. The trajectory presented a problem. Anything launched toward the Sun must travel at very high speed to avoid being overwhelmed by the Sun's powerful gravitation. And because the Parker probe had to pass so close, speed records would be broken. The Delta IV Heavy, fitted with a solid-fueled upper stage, was the most powerful rocket available at the time of launch. It was designed for lifting giant communications and intelligence satellites to geosynchronous orbits. The Parker probe is of modest proportions, and there was plenty of empty space after it had been encased within the Delta IV's launch shroud. The giant rocket was needed for speed. August the 12th, 2018.
7, 6.
The 90-year-old Eugene Parker was there to witness the launch of the Parker Solar Probe.
0. Liftoff of the mighty Delta IV Heavy rocket with NASA's Parker Solar Probe, a daring mission to shed light on the mysteries of our closest star, the Sun.
Fixed to the spacecraft was a plaque with a quote from Parker, "Let's see what we can find out." It was a fitting tribute to a significant figure in science. The PSP left Earth at around 57,000 kilometers per hour. Only the New Horizons probe, bound for Pluto, had a greater departure speed. But New Horizons, traveling away from the Sun, was constantly slowing under the influence of solar gravity. Traveling toward the Sun, the PSP was accelerating. After 8 days, it had already picked up 10,000 kilometers per hour.
Parker Solar Probe is the hardest trajectory that I've ever worked on. The folks at Applied Physics Lab have come up with a very unique trajectory where the spacecraft is going to use the mass of Venus to slow themselves down. And not only are they doing that one time, they're actually going to do that 7 times in a row over a space of 6 years in order to get the spacecraft perihelion, because we're orbiting the Sun, down below 10 solar radii. And therefore, when we pass very close to the Sun, which is the most massive object in our solar system, we are going approximately 430,000 miles per hour relative to the Sun.
It took only 53 days to make its first pass of Venus. Most Venus explorers had taken in excess of 100 days. A spacecraft operating in a weightless environment can be perturbed by the gentlest of forces. Even sunlight can nudge a probe off course. Accurate radio ranging techniques will reveal even the slightest divergence from the desired path. However, the PSP spends much of its time close to the Sun, an unfamiliar cosmic environment. Charged particles will distort positional information, and the probe will be out of contact as the Sun-Earth probe angle narrows. New ways of operating a satellite within this environment are still evolving. The Parker Solar Probe began its first pass of the Sun in November 2018, reaching a close point, perihelion, of 24 million kilometers and a top speed relative to the Sun in excess of 340,000 kilometers per hour. Researchers on the ground had to wait several weeks for confirmation that the spacecraft was functioning correctly and that it had recorded data. It was several more weeks before that data could be downloaded. The probe had passed through several magnetic switchbacks, sudden, brief reversals in the magnetic field lines. These could be the means by which the corona is heated to its extreme levels. To actively align its heat shield toward the Sun, the Parker Solar Probe uses a combination of rotating momentum wheels and thrusters. Engineers were delighted to learn that the craft was so well balanced it was using less fuel than expected for its alignment. Thruster fuel is the limiting factor in most missions. The following year, the Parker Solar Probe made 2 more passes, each one closer to the solar surface and with an increasingly higher top speed. In 2021, during its 8th perihelion, the PSP passed slightly more than 10 million kilometers above the surface at a speed in excess of 530,000 kilometers per hour, continuing to break its own records. NASA has frequently used the expression "touched the Sun," referring to this and subsequent close passes. This may be poetic, but a more accurate description is that the probe passed inside the Alphen surface, the region of the corona that is still gravitationally and magnetically connected to the Sun. It found a lumpy, uneven boundary, and at the closer distance, the magnetic switchbacks were now experienced as strong jets of high-energy particles. Researchers concluded that they must be driven by magnetic reconnection. At this distance, they had a clear direction that could be followed to their source: convection cell structures seen on the face of the photosphere. Tangled magnetic field lines push out along the edges of these cells, propelling charged particles outward. This was a breakthrough in understanding the solar wind. It also captured pictures of solar streamers, previously only visible from Earth during solar eclipses. The only pictures the Parker Solar Probe can deliver are from a camera with a sideways view. It was simply not possible to protect a forward-looking camera from the extreme temperatures. However, a European spacecraft, designed to work with the PSP, now provides images. The closest, most detailed pictures ever made of the Sun. The European Space Agency's solar orbiter had been in development since 2011. NASA was a junior partner in the project, supplying one of the spacecraft's instruments and providing launch services. However, it had been delayed while the spacecraft was extensively tested and retested.
8, 7, 6, 5, 4, 3, 2, 1, 0. And liftoff.
In February 2020, Solar Orbiter successfully began its mission.
To give us new images and a better understanding of our life-giving star.
During the development of the Solar Orbiter, there had been extensive collaboration between NASA and the European Space Agency to ensure that the Parker Probe and the Solar Orbiter would complement each other's investigations. The Solar Orbiter has 10 separate scientific packages: in situ instruments for registering the particles and fields that impinge upon it, and remote sensing instruments primarily for imaging the Sun across a range of extreme ultraviolet wavelengths. While it cannot pass as close to the Sun as the PSP, the Solar Orbiter still needs heavy-duty thermal protection. Thin sheets of titanium foil pinned to an aluminium honeycomb make up a heat shield with 5 peepholes for instruments. Its solar panels rotate to prevent overheating. Like the PSP, the Solar Orbiter used the gravitation of Venus to augment its orbit. During its initial cruise phase, it also swung back past Earth for added gravitational assistance. It's in a resonant orbit with Venus, and soon it will use that planet's gravitation to bend it out of the ecliptic. This tilted orbit will, for the first time, allow pictures of the solar poles. In September 2023, the Solar Orbiter returned this view at the 171 angstrom wavelength. It reveals the transition from the Sun's lower atmosphere to the corona. The waving, slender threads are plasma from the interior, following the changing magnetic field lines.
So it's very fascinating to see for the first time the high resolution of images of the solar corona. The images we are getting down now with perihelion are perhaps the best ever recorded. And so we are seeing stuff there that has not been recorded before.
At the same time these images were captured, the Parker Solar Probe was passing the Sun at just 7.26 million kilometers. By matching the data from both craft, solar physicists could use the Solar Orbiter to see the origins of the solar wind that was being recorded by the PSP. The Solar Orbiter also carries a coronagraph. It's a useful instrument for observing the corona, which is usually not visible because of its proximity to the brilliant Sun. The best coronagraph we have occurs when the Moon blocks the Sun during an eclipse. By sheer coincidence, the relative distances and the relative diameters of the Sun and the Moon allow the Moon to occlude just the Sun, providing a clear view of the parts of the corona close to the solar surface. but the observation time is limited to just a few minutes. Soon, a new pair of European satellites called Proba 3 will test a new technique for observing the corona. The occluding spacecraft will use lasers to accurately position itself 144 meters from the observing spacecraft. They will fly in precise formation with the occluder casting a tiny shadow upon the observer's instrument, accurately blocking the sun's disk. This will deliver images of the corona closer to the edge of the sun than have so far been available. It is this area of transition that solar scientists want to understand. Regular contact between the science teams of the Parker Probe and the Solar Orbiter are maintained to plan future joint investigations, especially when their craft will be in complementary positions. Solar researchers are hoping to understand any interconnection of solar phenomena so that they can build computer models that could be helpful in predicting the sun's behavior. This is how weather surfaces on Earth work. Powerful computers combined with extensive high-resolution data sets have seen great improvements in the accuracy of weather prediction. In the pre-technology world, solar weather resulted in beautiful auroras. Today, if a major coronal mass ejection unexpectedly collided with Earth, a variety of events could unfold. The International Space Station orbits at around 400 kilometers, yet there is drag from the very thin air that still persists at this height. To reduce friction, its solar panels are swiveled edge-on when the Earth blocks the sun. Even so, the space station loses around 75 meters in altitude every day, and regular boosts from visiting spacecraft or firings of its own propulsion system are required. Solar storms heat the upper atmosphere, causing it to swell. During heavy solar activity, the ISS has lost as much as 1,500 meters in one day, and waves of charged particles can disrupt sensitive electronics. Low Earth orbiting satellites are affected in a similar way, and without adequate warning, spacecraft have been lost. SpaceX's fraternal company Starlink owns 60% of operational satellites and continues to add more. The internet provider launches up to 60 Starlink satellites at a time to low Earth orbit. Each is equipped with an ion thruster, and they spread out, gaining height after deployment. Early in 2022, a moderate coronal mass ejection was detected from the northeast quadrant of the Sun. Several days later, Starlink launched 49 satellites. The timing couldn't have been worse. The satellites did not have the power to break free from the thicker atmosphere, and 38 of the spacecraft fell back to Earth. A study following another geomagnetic storm in May 2024 revealed that 2,000 satellites had to maneuver after being pushed out of position. In these crowded orbits, this type of event significantly raises the chance of collisions. In March 1989, after 2 coronal mass ejections, Quebec was blacked out as circuit breakers protecting the electricity grid were tripped. Long power lines and a unique geological substrate inhibiting excess voltage running to ground made the province vulnerable. There have been advances in power grid design and in shielding the delicate electronics necessary for communication with and control of spacecraft. Techniques for monitoring the sun's behavior have improved, but the experts know that a major plasma wave that directly hits the Earth could still overwhelm these precautions. And soon, for the first time since 1972, space flights will take humans beyond the protection of the Earth's magnetic field. The Artemis program aims to return astronauts to the Moon and establish a lunar orbiting outpost. Humanity's understanding of the Sun is basic. Close monitoring of its behavior and the accumulation of long-term data sets will give our technological world deeper knowledge of the star upon which we depend.